All right, good evening, everyone. Yeah, so I think we can get started. Let me just make these slides available for download as well. Right, okay, so for tonight, we're going to take a look at operational amplifiers. Now, I think for this one, I'm going to just jump straight into examples. There is a lot of theory that you guys can go read through. Yeah, so I would say go read through this, especially maybe look at how the null adjustment for op amps function. So yeah, but I would say that's also very important, and see how you can employ a null adjustment offset or null adjustment circuit. What I would want to say is so basically the textbook doesn't have the circuit diagram in it, and it does get it asked in the exams from time to time. Okay, so just maybe go look at this. And another thing that I also just want to make a note on here is the drift variation of your output. So this is part of something that we would call common mode. That's actually why we have your common mode rejection ratio for op amps. That's basically the ability of the op amp to reject noise and signal drift. And that's usually done because we make use of different, so basically within an op amp, you basically have two common emitter transistor amplifiers. And you basically, so if you have an error or you have some signal shift between the two transistors there, between your two inputs, that signal drift is getting amplified equally on both sides. And because we're taking the difference in voltage here in our output, that pretty much gets cancelled out. So that's what your common mode rejection ratio is. How well your op amp rejects noise and drift. Right, so I would recommend that you guys just go read through this. I'm not going to really spend time on this, because there's a lot of repetition here. So I would recommend you guys just go read through this. Okay, so what I am going to focus on, though, is just basically how op amps function. I'm going to take a look at a few examples, and just to kind of lay the groundwork here before we go into doing calculations and stuff. So what you guys do need to keep in mind is, if you use an op amp, so depending on which terminal you are inputting on, that's also going to determine how your output is going to behave. Now, for a moment, just imagine that you have infinite gain on the op amp, and that you're not limited by your supply voltages. So if I input a signal, well, I say infinite gain, let's just say it has finite gain, and I input a signal like that on the inverting input, then that's going to give me an output that's an amplified version of the input, but inverted. So basically, the positive of our input now is negative, and negative is now positive. Same thing with, you're going to have a similar thing with a non-inverting, so basically inputting a signal on the non-inverting input. So you guys will see that your output is pretty much just going to be an amplified replica, if you will, or an amplified version of your input there. If you put inputs on both inputs, so basically on the inverting input terminal and the non-inverting, so essentially what you're doing there is you want to amplify the difference between the two signals. But if these two signals are identical to one another, that is if your null offset is set to 0, your output is going to be 0, because you're basically taking the difference between these two signals and then amplifying it. And like I said, if it's two identical signals, they're just going to cancel out. Now, if we phase shift one of those signals, then again, you're just going to get the two. Yeah, you're basically just again going to amplify the difference between the two. Right. Okay, so let's take a look at the inverting amplifier. Now, there is an exercise in the textbook as well. It pretty much has an exercise. Yeah, so the exercise has an exercise on each amplifier in the textbook. So just give me a few seconds here to get everything ready. Okay, so for the inverting amplifier, so as you guys can see, yeah, so that will be what we call your gain part. So that's just the ratio of feedback resistance to input resistance multiplied by the input voltage. So also take note of the negative sign there to account for the inversion that occurs here. So you guys can see your input signal is applied to the inverting input of your op amp. So inverting amplifiers typically are characterized with high gain. So usually your feedback resistance is significantly bigger than your input resistance. And yeah, so one of your design considerations, by the way, when working with amplifiers is to just keep in mind what your supply voltage to the op amp is as well, because you can't amplify more than the supply voltage, right? You will violate the laws of energy if you do that, if you somehow manage that, which, by the way, you will never manage. But anyways, um, yeah, so you can actually then simplify that formula for the output voltage as gain times the input voltage. Right, so something that's actually also interesting here with an inverting amplifier, I just want to let you guys take note of it. You can actually manage to make this what we would call an attenuator, so meaning having gain less than 1. So if you make the input resistance here bigger than your feedback resistance, not necessarily, yeah, it's not usually done, but it is something that you can do with an inverting amplifier. Whereby in contrast to the non-inverting amplifier, your gain will always be bigger than 1. Right. Okay, so with the non-inverting amplifier, yeah, so you guys will see the gain in this situation is then 1 plus the ratio of feedback resistance to input resistance. And also take note, this is positive, so your input signal is not going to be inverted after amplification. Yeah, and again, just take note that the input signal is applied to the non-inverting input there. And the inverting input is pretty much pulled to ground through your input resistance. And yeah, so the statement, yeah, so there's a statement here that the overall gain is higher than that of the inverting amplifier. Now that will depend on how much gain you are actually speaking of here. If you speaking of gain in the single digits, then yes, a non-inverting amplifier is going to have significantly more gain than an inverting amplifier. But if you speak of gain, let's say maybe 100 or 200, then having a gain of 101 versus 100 is not really that big a difference. So yeah, then it doesn't really matter that much. But anyways, I think let's maybe take a look at a quick example as well. But I think let's maybe do the summing amplifier as well, because the summing amplifier is essentially an inverting amplifier with multiple inputs, right? So you can use superposition in this situation to basically calculate what your output voltage is. So you can go and calculate the contribution of each input voltage in what output voltage it would result in. and then just add everything together. All right, so that's essentially what's done here. So you guys can see there's the contribution of the first input voltage and first input resistance, contribution of the second input voltage, contribution of the third input voltage, and then you end up with a general formula that will look something like this. So simplifying things a little bit, so you take out the negative sign and the feedback resistance, which will be common to all of the inputs there. And then, then that's your general formula. So your gain in this sense, so you're going to have a gain for each input. So gain for input 1, let me maybe use the same colors we have there. So the gain for input 1, it's going to look something like that. That's going to be your feedback resistance divided by your first input resistance. For input 2, your gain is going to be the feedback resistance divided by your second input resistance. And then lastly, your gain for your third input is then going to be feedback resistance divided by your third input resistance. Now you can get a situation where if you make all of the input resistors the same size, you then end up with a formula like this, where it's RF divided by R, which coincidentally, this is going to be your overall gain, multiplied by the sum of input voltages. Right, so that actually makes things quite a bit easier than having different input resistances. Okay. Okay, so let's maybe do another circuit, and then we can do a few examples. Voltage follower, pretty easy. Not really any calculations involved here. So voltage follower, you pretty much just have feedback to your inverting input, and your input voltage is applied, or your input signal is applied to your non-inverting input. Okay, so one of the things you guys will note here is that the gain for this circuit is going to be unity or 1. So output voltage, input voltage is the same. So I would wonder, okay, why would you do this? There are some reasons for this. Main reason being is that this circuit is usually used in impedance matching. So I'm just going to quickly skip back to the ideal characteristics for an op-amp. So in an op-amp, you want really high input impedance and really low output impedance, which is what the voltage follower gives us. So this is especially useful if you want to connect to amplifiers that are pretty much in cascade with one another or in series with one another. So if your first amplification stage, let's say, has a high input impedance, or rather, let's say it has a low, actually I'm getting the things wrong here. So let's say it has a, so let's say it has a high input impedance, your first amplification stage. So let's say call that amplifier A with a high output impedance, and we connect it to amplifier B with a low input impedance. Right, so those two amplifiers are then mismatched to one another in terms of impedance. So meaning amplifier B is going to pretty much overload, or so it's going to cause excessive load on amplifier A. Now, basically where the voltage follower comes in is basically in between here, because the voltage follower itself is going to have a very high input impedance, which means it will then be matched to amplifier A, and its output impedance is low, which means it will then be matched to amplifier B. So basically, that's what's meant with impedance matching. Can also use a voltage follower as a buffer circuit when you have two circuits that need to be electronically isolated from one another. So in essence, what you basically want to do is you want to protect your first circuit. So basically the circuit here, so let's say amplifier A, is the circuit that we want to protect. We don't really care what happens on circuit B there. Circuit B, so this could be a typical example of where you maybe have some load or sensor that you need to power or something like of that nature, right? Okay, so that's your voltage follower. So I'm tempted to do the audio amplifier as well, as it's very similar to the inverting amplifier. But I think let's quickly do examples and then we can come back to this thing. Okay, so I found something. Okay, so just to demonstrate the inverting and non-inverting op amp, and then the summing amplifier, then yeah. So exercise 3, number 3.12 is what we're going to take a look at first. Yeah, so it's gonna look like I'm jumping back and forth here on exercise because the textbook has some of the stuff in a weird order, so just bear with me here. Okay, so let's see. Okay, so we're given a feedback resistor, RF. I'm going to lose my patience here. Why is my computer doing this now again? I didn't do this last night. Just give me a few seconds here. See if I can, because the computer, because I'm using a tablet, is a text field that jumps up. Okay, so the feedback resistance, that is then 100 kilo ohms. Input resistance, that's going to be, or input voltage, okay, shoot, I thought it was resistance there. So the input voltage signal is then given to us as 125 millivolts or 0.125 volts. So we need to go determine what the output voltage is going to be for a non-inverting op amp and an inverting op amp. Interesting. We're not given input resistances. Let me maybe make 100% sure that we're not given that. In fact, we're given 3 input resistances. It's just on the next page. So I'm going to pick one of the input resistances. Let me maybe copy them to the whiteboard here as well. These resistances are given just on the next page. So you're pretty much going to repeat the exercise 3 times. I'm just going to do it for one of the resistances. So for now, I think let's take a look at the 50 kilo ohm resistance there. So for 3.12.1b, so for a non-inverting op amp, so basically if we write down the output voltage, that's 1 plus RF over Rn multiplied by the input voltage. Now that's going to be 1 plus, 100 kilo ohms. So it's 100 kilo ohms divided by 50 kilo ohms. So the kilo ohms actually cancels out. So it's 100 divided by 50. And our input voltage, that's 0.125. And 100 divided by 50, that's going to give us 2. So we have a gain of 3 here. So 125 times 3, that's going to give you 250, 375, or 0.375 volts. Okay, so that's for a non-inverting op amp. Then for the inverting op amp, so 3.12.2, number B. So again, we're still going to use the 50 kilo ohms. Remember your negative sign, so minus RF over Rn. multiplied by the input voltage. So that's going to give you minus 100 kilo ohms divided by 50 kilo ohms. Again, the kilo ohms cancel each other, or the kilo values. Then 0.125. Again, 100 divided by 50, that's 2. So that's 2 times 0.125, which is minus 0.250 volts, or 250 millivolts, however you want to write it down. Okay, everyone happy so far? Everyone good? Okay, so then let's take a look at another example. So let's take the summing amplifier. I think in this exercise 3, that's going to be number, just check here, number, let's see, there's actually quite a few examples here, but in any case, so number, say 3.9. Okay, so this is a bit of a weird question. I think the author might have made a mistake here in formulating the question. So I'm not too sure what's, I myself not 100% sure what's going on here. But let's take a look at it. Okay, so yeah, so number 3.9, exercise 3. Right, so again, if we start with the output, yeah, so we're basically given the output from 3 sensors, meaning this is going to be the inputs to your op amp. Now they tell us here it's applied to a non-inverting operational amplifier. That's actually bogus. You guys don't do non-inverting summing amplifiers. You only do inverting summing amplifiers. And we need to go determine the output voltage if this amplifier uses a 50 kilo ohm feedback resistor and the following input resistors. Now, they give here different input resistors. So the thing is, I don't know if the author meant that that is R1, R2, and R3. I have no idea, but that's how I'm going to treat it. Or if it's an exercise in redundancy whereby basically that 15 kilo ohm is R1 equals R2 equals R3 equals R, and then do that for each and every single one, which I think is a bit of a, yeah, it's a pointless exercise. It's like I said, it's a exercise in redundancy. So I'm going to not see this as separate exercises. I'm going to view this as R1, R2, and R3. So our 3 input resistors. So let me just draw the circuit so that everyone knows what we are working with here. And I am going to throw this computer, kick it down the street because it keeps on popping up this stupid writing to text window. Why every time I hover it does this? Okay, so that's going to be on the inverting input of your op amp. And your non-inverting is going to be grounded as your output. There's your feedback. Okay, I forgot the resistor, so I'm just going to squeeze it in there. Right, so we are going to need to use the generic formula here. So your output voltage is then going to be minus RF with the ratio. Yeah, so basically, first of your first input's contribution, then your second input's contribution, and then your third. So yeah, so you can actually, to the circuit, you can add a fourth, a fifth, and a sixth input, as long as, yeah, so just keep in mind that you can only amplify up to your supply voltage. So if your supply voltage is 15 volts, then if the sum, yeah, so if the sum of these input voltages amplified equals more than 15 volts, you're going to saturate your amplifier, which it's not going to destroy the amplifier, but you're not going to get a, you're not going to get an accurate result on your output. Then let's see here, RF. We were given that value as 50 kilo ohms. So if we just take a quick moment here and see, we can see that all these values are kilo ohm values. Right, so that means that's going to cancel out. So 50,000 versus 15,000. Yeah, so basically, if you think about it, 50,000 divided by 15,000 is the same as 50 divided by 15. Right, so we can just get rid of the thousands there. Input voltage, that was 4.5 millivolts. As you can actually kind of choose how you want to do the cancellation here. So let's keep it yeah, so if I keep it just as is, just keep in mind that the voltages we're working with here are millivolt range values. I think let's maybe make it easier for ourselves, just so that you guys know. R1, that's 15. R2, okay, so V2, that's 6.5 millivolts divided by 25. And that is 40. Right, so now we can actually go and calculate this. Let's see, that is 4.5 divided by 15 plus 6.5 divided by 25 plus 2.5 divided by 40 multiplied by 50. So this is going to give you minus 31.125 millivolts. Or you can write it as minus 31.125 times 10 to the minus 3 volts, however you want to write it. Okay. Okay, everyone happy so far? So far it's been not too difficult. Okay, so I think yeah, I think let's take a look at the next amplifier circuit here. And that would be the audio amplifier. Now the audio amplifier, so you guys will kind of notice that it is in the form of what we would call a differential op amp. But yeah, so we're not really interested in its differential input, because pretty much the the non-inverted, sorry guys, so the non-inverted input is pretty much clamped at 15 volts. So essentially you have a 15 volt offset here on the output, pretty much permanently there, because it's, yeah, so it's inverting, so it's going to be a minus 15 volt there. In fact, I think that's actually to counteract the inversion. But the thing is, usually this op amp is going to output to something like a transistor that's driving a speaker. And yeah, so that transistor is going to need a positive bias voltage. You can't bias a transistor with a negative voltage unless it's a PNP transistor, but usually NPN transistors are used. So you can then use a single transistor to drive a speaker instead of using two transistors. But in any case, so essentially, yeah. So essentially you end up having an inverting amplifier here. And so basically having your signal inverted here for audio, it really doesn't matter. You can have it inverted, non-inverted. It's not going to impact your sound quality. It's not going to impact what the sound sounds like. It's actually somebody already on it's actually quite a few people on YouTube already that did that experiment. So there's something that is worth to go check out and witness for yourself. Right, I'm not going to spend too much time here. I think I'm also going to skip here doing the example because there's actually another circuit I want us to tackle. I see we do not have tons of time. All right, so for this circuit, what is important though is so working with the input and output and gain, for instance. So the gain for this circuit, that's just going to be your feedback resistance, RF over Rn. So this resistor here, that's RF, actually it is labeled there, and then that's your input resistance right there. Okay. So your gain is the same, so maybe just put a negative sign there. So it's the same as for an inverting amplifier. However, you have these capacitors that are extra to the circuit. So capacitor C1, for instance, so these would be your coupling capacitors. So essentially C1, what it basically does, it blocks any DC from going to your inverting input. Now, or blocks, or rather, let me maybe say block signals below a certain frequency to to prevent low frequency noise or low frequency signals to go onto the inverting input and then potentially getting amplified. And the same with C2 there as well. So C2 is also kind of act as a low pass filter there, or not low pass, high pass filter is what I meant. Okay, so so as you guys can see, that is going to be dependent on frequency. That frequency is going to be pretty much your minimum frequency that you're going to let through. And so as you guys can see, for C1, that's also going to be dependent on your input resistance, and C2 will be dependent on your load resistance. So your load resistance not indicated very clearly in the drawing, but that there is your load resistance. Okay, so that's pretty much so it's just calculations added on top of the already existing inverting amplifier calculations. All right, and then you also get the comparator. So basically what the comparator does, it basically, if you just want to discriminate between two different inputs, or if you want to discriminate between an input and a reference, so for instance, you have a sensor checking whether your water level is at a certain point, but you don't care what your water level is. You just want to know if it will drop below a certain value. So you either want a true or false answer. Right, so then you can use a op-amp comparator. Now, this circuit is not necessarily so this is not the only circuit for an op-amp comparator. You can swap the input and reference around, meaning in its current situation, if the input is bigger than the reference voltage. So if we take a look here, so for instance, if this is our reference, actually no, that is our reference, and this here is our input. So you'll see that while our input is lower than the reference, the op-amp's output is going to be high. And then the moment so in this part here, your input is now bigger than the reference. So that's then going to give you it's going to drive the output then to minus VCC. So it's basically going to saturate the amplifier the whole time. But like I said, this is if you just want a true or false answer. It's a very helpful circuit if you're working with digital circuits and you just want a 0 or a 1 as your interpretation there. Right. So again, if the input goes below the reference higher output, you can get the inverse as well. So like I said, you can have just swap the inverting and non-inverting terminals there with the input and reference. That also just means that this curve is just going to be inverted as well. But yeah, that's just the difference there. It's just something I picked up with N6 and N5. For some reason, you guys need to know this circuit on N5, and then on N6, it's the other one with the terminals connected the other way around. But yeah, it actually doesn't matter. The function is essentially the same. All right. Okay, then you have your differential amplifier or subtractor. So essentially what we're doing in this is especially a very handy amplifier if you want to say you want to measure the voltage across a component in a circuit, and you only have your standard oscilloscope probes, meaning that the one end of your probe is grounded and the other end is not. So you can't, so for instance, if you have components like this, so for instance, let's say we have an RLC circuit here. So with your oscilloscope probes, you can't, so let's say we want to measure the voltage across the resistor only. So you cannot measure like this, because the one terminal of your oscilloscope probe is grounded. So you're basically shorting out the other two components there from the circuit. So this is where this op amp comes in handy. Now you can connect the op amp across the resistor there. You're basically measuring the voltage drop across the resistance, or the difference in voltage levels. So basically V1 is going to have a different value to V2. So you essentially, V1 is basically the voltage from there to ground, and V2 is the voltage across your capacitor and inductor to ground. And then basically you're just taking that difference, amplifying it, and that then goes to your oscilloscope. And you can actually then measure the voltage across your resistor that way. Right. So, and that is done without shorting your circuit out. Right. So that's where differential amplifiers are really helpful. Another name for these as well is an instrument amplifier. So that's also another name for them, but that's how they function. There's the generic formula. If the feedback resistance, so R3 is also usually equal to the feedback resistance here. And we also usually make R2 equal to R1 as well. Just makes life a little bit easier. And then you have that generic formula. But if you make all the resistors the same value, then you essentially, your output voltage will just be your difference between your two input voltages. Okay. Then the two circuits that I want to get to is the differentiator and the integrator. Now, the differentiator and integrator also have practical circuits associated with them as well. And this is just due to some gain issues at lower or higher frequencies. So for instance, for differentiator, guys will see that so if we take a look at this formula here, your gain is essentially, how can I say, determined by the reactance of your capacitor. So you can actually write you kind of have a dynamic gain, if I can put it that way. So I'm going to have RF over XC essentially. But now the problem that you run into is that your capacitance or your capacitive reactance is dependent on frequency. So if you input a frequency here with a high frequency, so if your input frequency is very high, you're going to have a very high gain for this amplifier, because you look at XC, that's 1 over 2 pi fc. So meaning if the frequency goes up, xc goes down, which means the gain of your amplifier shoots up as well. So differentiators are typically then susceptible to high frequency noise. Now, the way we get around this problem is by introducing a resistance series with the capacitor, and that will then give you a fixed gain of RF over RS. So that's going to be your minimum gain that you're going to have there. All right. Okay, everyone happy, everyone good. I'd say minimum gain is actually going to be your maximum gain. So your gain is pretty much going to be capped at that value. Okay, so that's for the differentiator, and that's its practical circuit. Its normal circuit, you just ditch RS, then you have the theoretical circuit. All right, so here we do have a bit of an example, and this is actually an example from the textbook as well. So we have a 1 megahertz signal applied to a practical operational differentiator with a gain of 20. We need to go calculate the values of the feedback resistor and the input resistor if a capacitor value of 1 nanofarad is chosen. Right, so it's a bit trickier to immediately figure out what we need to do here. So one of the things that we can go and do is, in order to get maybe to go and calculate the feedback resistance, is that so basically what you guys kind of need to notice here is this combination there. That's pretty much the same formula for time constant. And you can actually use your frequency here in this case to help you out. So you can say maybe the time constant is equal to your frequency, or rather 1 over your frequency. And that's going to give you a period here of 1 microsecond. And then you can equate that 1 microsecond to your feedback resistance multiplied by the capacitance. But because we now know that value, and this is given to us, we can go calculate RF. And manipulating the formula then to calculate RF is then going to give us 1 kilo ohms there. And then because we now know what RF's value is, we can go calculate our input resistance using the gain. So our gain was given to us as 20. So manipulating that formula is then going to give us the feedback resistance divided by the gain, which is 1000 divided by 20. And that's just going to give us 50 ohms. Right. Okay, so this is the circuit that I actually want us to look at, and that's the integrator. Now, I have a bit of a problem with this statement. So if you put a sine wave into an integrator, or a square wave, you're going to get a sawtooth or triangular waveform. For the sine wave, you're just going to get a phase shifted sine wave, so it's not really going to be a sawtooth or triangular waveform. But anyways, I can get a phase. It will be phase shifted. It's not going to increase in frequency or anything like that. Anyways, so its general formula will look something like this. So it's 1 over RC, and then you take your input voltage and integrate it. Now there is a certain way we need to integrate, especially for this subject. So you guys need to be able to integrate a square waveform. But this is the example I actually want to get at, and then we can do this. But I also want to mention something that is not mentioned in the slides, and that is also the addition of a practical, or rather the practical circuit. So usually in the practical circuit, we also add a feedback resistor, which we, for some reason the textbook also goes and mentions it as RS. I think the reason why I don't have it in the slides, in the textbook it looks like it's part of an example, but it's a mistake. I'll show you guys in a moment. So so this is also to limit the gain. So whereby the differentiator had a problem with high frequencies, and increasing the gain at high frequencies. And the integrator has the opposite problem. It tends to significantly amplify DC and low frequencies. Right, so you can get a DC offset from your input signal, or your output signal will generate a DC offset, and that will just get bigger and bigger as the frequency on your input gets lower and lower. Right, so that's basically to limit that, limit the gain for DC and low frequency inputs. Okay, but I just want to quickly show you guys where in the textbook this example is, and then I'll actually see, yeah, we don't really have tons of time, but maybe let me just show you guys what you have to do here when doing this exercise. But I just want to show you guys the example of the practical integrator here. There's also a point, a minimum frequency at which integration will occur. So that's something you guys will be able, or will need to be able to calculate. Let's quickly do this. Okay, so this would be example, yes. Right, so yeah, so here we have the integrator. So there's the example that I want us to kind of look at, but I'll use an exercise to demonstrate this. Yeah, so it's basically you're going to do piecewise. I say piecewise. Yeah, so you're basically going to integrate a piecewise function. It's basically what you're doing with a square wave here. So yeah, so here's the practical circuit or the practical integrator circuit. So again, the gain is just going to be RS over R1. So you're basically limiting the gain to just that number. And yeah, so the value of R2 in this sense is then mathematically given by this formula here. Yeah, and I actually forgot R2 is this resistor here on the non-inverting input. So have to also account for that. That's calculated as if R1 and RS are in parallel together. And then you have your frequency at which integration will occur. So essentially what this practical circuit does, it prevents integration of a signal below a certain frequency. Right, so you're basically creating a cutoff frequency or a frequency at which integration will start happening. So if, let's say, the frequency is 100 hertz, so everything under 100 hertz is not going to get integrated. Only a signal 100 hertz and above will get integrated. Right, so there is an example in the form of example 9 demonstrating this. So there's calculating R2 and then calculating the frequency at which integrating will start to occur. So this particular example, you only have integration from 159.134 kilohertz. Okay, so yeah, so let's maybe take a look at another example. I think while on the textbook here, I'm just going to scroll down. Sadly, I don't think we're going to have time to do the filter, so I'm going to leave that to you guys to just check out and go through in your own time. It's not really, yeah, the calculations there are not really intense. So yeah, I think you guys will be okay on that front. Not really hectic theory at the yeah, so we don't really have super duper heavy theory for that at the moment. We'll do that when we get to resonance for AC circuits. I think where's that example now? Sorry guys, I'm just looking for that integrator example. I think I'm scrolling past it now the whole time, but I know it's here, the exercise. Maybe it's the very last exercise here. Okay, it's one of the last ones. So it's 3.18. So let's take a look at that one. I know we're going to go over time here, so I'm going to try and be fast with this one. Okay, but I'm not going to work with the values. I'm just going to work with RC the whole time. It's just going to make things a wee bit easier. Let me just quickly jump to the whiteboard here. Okay. Maybe we can calculate this thing completely. Right, so what usually, for me, what can help you, so what can help a little bit is by drawing out what your input more or less looks like. Let me maybe do it quickly like this, just before I lose my temper with this computer now. Okay, so our input voltage is going to fluctuate between positive 1.5 volts and negative 1.5 volts. So you just have some sort of more or less thing going on here. Let me just do it this way. So there's our input voltage. So say that's maybe 1.5 volts. Let me maybe make this bigger. Say there, there, there. Right, so now for some reason now my tablet dies because I used my mouse. So essentially, yeah, so that's then plus 1.5 volts there, and that's going to be minus 1.5 volts. Right, so our output, I'm just going to plot then here on another axis. And I already actually know that the output here is going to be negative. Because essentially what you're going to do is when you're integrating this, essentially this 1.5 volts is the slope of the line that you're going to draw here, right? So you're going to have a positive sloping line for the plus 1.5 volts and a negative sloping line for the minus 1.5 volts. Okay, so if we do the calculations here, so if we do for the first part, so this thing is at 800 hertz, so it will help you to calculate the period of the signal and the half period of the signal. So 1 over 800. So that's going to give you a 1.25 milliseconds. And the half period of that is 625 microseconds. So you can actually write it down as I'm going to keep it in milliseconds, 0.625 milliseconds. Right, so that's actually very important. So that's where your half period is going to be, is there. And then you're going to have one full period. Okay, so the first part that we need to do here is we need to go, I would also say maybe go and calculate what this value is beforehand, 1 over RC, because then you can just substitute it in everywhere. I am going to throw away my computer. So that's 1 over 15 times 10 to the 6 times 10 times 10 to the minus 9. Right, so that is essentially minus 9, that's going to be minus 3. So that's essentially 1 divided by 15 divided by 10 multiplied by 1,000. Right, so that's going to give you 6.667. And yeah, so now we can actually do our calculation here. So for a start, you're going to work between 0 and t over 2. Sorry, for t equals 0 to t equals 0.625 milliseconds. Right, so essentially your output voltage here then, so essentially that's TA and that's TB. So we're going to calculate up to TB. That's minus 1 over RC, and we're integrating from 0 to 0.625. I'm going to keep it in milliseconds. So the value that we are going to get is going to be a millivolts value. Okay, so in any case, we have the voltage, our input voltage, that's positive 1.5 volts, minus an initial voltage. So we don't have an initial voltage, so that's 0. Or is that plus? I think that's plus, not minus. Any case, so so that's going to be minus 6.667. Integrating 1.5, that's going to be a 1.5 T between 0 and 0.625. That's going to be 1.5 times 0.625 minus 1.5 times 0. That's going to give you negative 6.25 millivolts. Right, so yeah, so that's going to, I'm just going to randomly select it there, and then that's not a curved line, but it's a straight line from there to there. Okay, so I hope you guys are still fine, and just bear with me, we're almost done here. So for the second half of the period, so basically the output is going to change a wee bit. So now, this is now going to be, I should have actually said maybe the output at 0. At 0.625 milliseconds. This is going to be the output at 1.25 milliseconds. Right, so again, that's going to be minus 1 over RC, integrating. So this time we're integrating from 0.625 to 1.25 milliseconds. So again, milliseconds times volts is going to give you millivolts. So we just need to keep that in mind. And this is then remember, a negative 1.5 volts. So actually the negatives here are going to cancel out, because you can actually take out that negative from the integral. So that will cancel with that, and that will just become positive. And then we need to add our initial voltage. So this is now our initial voltage. So that's now going to be minus, or actually plus, minus 6.25. Okay, so that's then going to give us 6.667 multiplied by 1.5 T, and 1.5 T sits between 0.625 and 1.25. And then minus 6.25 millivolts. Right, so this here, that's going to be 6.667. And this is going to be 1.5 times 0 times 1.25 minus 1.5 times 0.625 minus 6.25. Right, so if you guys calculate this now, that should give you 0. So that's 1.5 times 1.25 minus 1.5 times 0.625. Yeah, that's going to give you 0. Okay, so your input is then going to go back to 0. Right, so that's pretty much just going to repeat itself for every subsequent input waveform. So if we had a bit more input waveform here, then your output is just going to then just follow like that. Okay. So this is then minus 6.25 millivolt. Okay, cool beans. Everyone happy? Guys understand where that is going? Okay, so if you guys don't have any questions, I bid you guys a good evening and a good week. I'll see you guys next week, same time, same place. Cheers. I'll load the notes onto the chat room now as well. All right, cheers, guys.